Welcome on stage.
Okay, thank you, and hi everyone. So the intention here is that this will be an introduction lecture to zero knowledge proofs and succinct arguments. So if you are not familiar with proofs and or you have a bit of shaky foundations, I'm not quite clear on the definitions and so forth, this is the lecture for you. Okay, so let me share my slides.
Yes, let's see if that works, and then I'll leave you on stage.
Yeah.
For everybody else, two things that I want to, while Jens is getting ready. If you have any questions, please make sure to post them in the questions tab on the bottom right side. Jens will go back to them at the very end during the Q&A session. So if you have any questions, please post them in the questions area. If you have anything in chat, we have both Erik and Jente around who will be able, and myself as well, obviously, we'll try and help you out. So questions tab, everybody. Thank you. All right, let's wait.
Okay, so I hope you can all see my screen.
Perfect. Take it away.
Okay, cool. Okay, so what is this? Sorry, why does it autoplay? Okay. Okay, so the problem we're facing is that there are lots of statements you can make when you're in an online context, right? And those statements may be true or they may be false. And the question is then, how can we verify those? And we may have some digital evidence why this is true, right? So if you're over 18, well, maybe you have some biometric data which is stored on the chip on your passport. And if you're a registered user to a website, you may have some login credentials and so forth. So the question then is, okay, how can we use that data to prove that the statement that we made is true? And there are sort of two concerns here we could have. One is that the data may be private, right? So for instance, if you're participating in an election and you've encrypted a valid vote, then sure, you want to show that you're following the protocol, you have actually encrypted a valid vote, but you do not want to disclose which candidate you're voting for, right? So that's clearly a privacy concern. You cannot just reveal people's vote. There's also another issue which may appear, which is that the data can simply be overwhelming, right? I would love in the future that we could have everything is verifiable. You could verify that every digital action a state has taken is lawful, right? But that would probably involve an enormous volume of data, and that would be overwhelming. So we would need to be able to verify that in a more efficient manner than just disclosing and looking at all the data. Okay, so let's talk a little more technically speaking about what is going on here and what is the abstract view. Okay, so in the following, I'll be referring to instances, which is what we're making a statement about, and witnesses which testify to the statement being true. And we can define a relation that represents sort of like valid pairs or like instances that have a good witness for them. Okay, and I'll assume throughout that there's a program that could in principle decide whether that is true or not. And we can then define L to be a language of instances that are true, right? So in other words, instances that have a witness in the relation. And that may not be something that's efficiently decidable, right? So if you claim that a Sudoku puzzle is solvable, that may not be so easy to decide, but if you provide actually a solution, a witness to it, then it may be easy to decide. And the statements that we are making is on the form that the instance belongs to this language. So in other words, it represents this claim that there's a witness in this relation. Okay, so I want to go through sort of like why this is actually a very general framework that can capture all sorts of statements, okay? And the way I'm going to do that is I'm going to talk about CKVMs, which is something that we are working at my company Nexus, but also many other teams are working on. So, and a virtual machine really represents completely general computation, right? So here I'm going to think about a virtual machine that takes as input a program and some explicit input X and maybe some extra input W and produces some output Y. And the question we're going to ask ourselves is this a correct computation? So in other words, you can think of the instance being a representation of the program and the explicit input X and the output Y, right? And the claim that this is correctly computed in the virtual machine. Okay, and if there's some auxiliary input also, then it may not be easy to verify whether it's true. Even without an auxiliary input, it may just be computationally burdensome to verify that this is true. Okay, so a CKVM then sort of like runs a VM, but also attaches a proof to the output that shows that it's indeed correctly computed, right? And then there's a corresponding verification algorithm that can decide, you know, is this a good proof or not for the output being correct. Now, the cool thing about these proofs is that they may be succinct, right? So what does it mean that a proof is succinct? It means, first of all, that the proof is small, okay? And they can really be extremely small. Like for a huge computation, it may still be that the proof is just in the order of hundreds of bytes. And second, partly because the proof is so small, and partly because the verifier doesn't actually need to see this auxiliary input W, the verification time can also be independent of the program's execution time and this size of the auxiliary input, right? So it may be much, much faster to verify than to compute. So even if you gave all the evidence and said you can compute yourself, that might be a much more burdensome process than just verifying a succinct proof. Okay, so if we can construct these kind of succinct proofs for correct execution of a virtual machine, right, then we have something really general. We can prove basically that any computation is correct. And in other words, we can prove basically any kind of statement that people would want to make. Okay, and I want to stress that there's sort of like two ways that reasons why people are interested in this. One is for scalability, just that it's really fast to verify, right? So you don't need to recompute, you just check the proof. And that may be much faster than computing on the data yourself. And the other reason could be privacy, that the proof could be zero knowledge. If it hides this auxiliary input W, maybe that's important, maybe that contains confidential information. Okay, now I want to admit here that CKVM is sometimes a misnomer because it's not always the CKVMs out there you see that are actually zero knowledge. Okay, sometimes we're just interested in them for the sake of scalability and we don't actually build zero knowledge into them. Okay, so let's think more generally about a proof system for a relation, right? Which could be one of these relations I just described. Okay, so in general, the picture here is that the prover has an instance and has the witness, whereas the verifier just has the instance, right? And the verifier and the prover then interact with each other, and at the end of the day, the verifier might say, yes, I believe the instance is in the language, or no, I don't believe that a witness exists. Okay, so some of the fundamental properties we want for a proof system is that it's complete and sound, right? So in other words, if it's a true statement, then it should be possible for an honest prover with a witness to convince a verifier. And on the flip side, it should be sound that if it's a false statement, then a cheating prover cannot convince the verifier. Okay, a proof system may or may not be zero knowledge, right? So zero knowledge is basically that saying that there's also a privacy aspect to it, right? Roughly speaking, that the verifier learns nothing else except the fact that instance is in the language. Okay, and there's sort of two variations of this that people often use. One is honest to verify zero knowledge, that a verifier that follows the protocol but is just curious, doesn't learn anything from the interaction with the prover. And then there's a stronger form of zero knowledge that even a verifier that may actually be deviating from the protocol can still not extract any information and extra knowledge from the prover. So of course, the verifier will learn that the instance is in the language, that it's a true statement, but we're just saying that the verifier will not learn anything else beyond that. Okay, so that's all like finishes the description of the core security properties that we want. Now I want to talk a bit about the efficiency of a proof system. And so like 4 core efficiency parameters that people tend to look at is, first of all, the amount of interactions, so how many messages are going back between the prover and the verifier. Secondly, the communication, so how many bits are transmitted in total. And then you could be interested in what is the verification cost and what is the proving cost, right? That could be measured in different ways. One would be how much time does it take to verify, how many steps on a machine does it take to prove something. But you could also be interested in other metrics, such as, for instance, the memory consumption. So a special type of proofs is, of course, like those that are ideal with respect to interaction, right? So non-interactive proofs. Non-interactive here means that the verifier doesn't actually have to send anything to the prover. So the prover can just compute the proof directly and then send it to the verifier. And non-interactive proofs are desirable because they can be computed without having a verifier that's online and interacting. Also, if it's non-interactive, right, then you can copy it, you can distribute it. So many people may be verifying the same proof. You just have to compute that proof once. Okay, and that's all like brings me to a couple of terms that you may have heard about before, right? SNARKs and STARKs. So I just want to demystify what those are. So a SNARK is a succinct non-interactive argument of knowledge, right? So succinct means that it's really small proofs and very efficient verification. Then it's non-interactive, so just a single message. There's no communication back from the verifier. And then it's an argument of knowledge, which is sort of like a strong version of soundness. Not only does a witness exist, but also that you sort of like a constructive proof that this witness exists, right? A SNARK doesn't have to be zero knowledge, and often it is. If people really want to emphasize, they write a zk-SNARK. Okay, another term that often appears in this community is that of a scalable, transparent proof of knowledge, a STARK, right? Scalable means that you have very efficient proof computation, and transparent means that you don't rely on a trusted third party to generate a setup, right? And this is sort of like in contrast that there are some proof systems where you sort of like assume, first of all, that there's some setup that has been generated, maybe some group elements with a specific structure, something like that. And both the prover and verifier will trust that those are correctly generated and have access to them. In a transparent proof, you do not make the assumption that there's a trusted third party that would generate that setup. So if there's a setup, it has to be sort of like a trustless setup that everybody can look at and just say, yes, this is an okay setup. And then it's also an argument of knowledge. So that's the ARG again, right? And usually it depends a little on the details of the definitions, but usually a STARK is also a SNARK, but not necessarily the other way around. Okay, so what does it look like today, right? So it's really prover efficiency that's a bottleneck, right? So we have non-interactive proofs. We can make them extremely succinct, so a few hundred bytes, even if you have like this enormous computation that you're trying to verify, or a very complex statement you're trying to verify, then it could still be the proof size is just a few hundred bytes. And verification time can be extremely fast as well, because you only have to check a very small proof and potentially a very small instance. So the remaining question really is, how fast can we prove things, right? And the cost for prover is typically very big and much, in the case of CKVMs, much larger than if you're just doing native computation. So, and when people realize how big the overhead is, I think it's good to sort of like keep a historical perspective of like, you know, how expensive was it to prove things back in the day, right? So in the 80s, when people first started thinking about proof systems, really, they were not thinking about any bounds on the prover. It would have like infinite time available to it. So anything would be really expensive to compute. And then, so like slowly, there were more and more applications where we found efficient proofs. So identification schemes was something we could do in the 90s. In the 2000s, I was working on voting schemes, and that became something you could do efficiently. In 2010s, something like mixedness was still a complicated kind of thing to prove, but now you could prove them as well. In the 2020s, succinct proofs have really become so like something we care about in the blockchain space, right? And we're so like getting to the point now we can actually efficiently prove the kind of things that people care about in blockchains, correct smart contract execution and things like that. And then, it's still open where we'll be in the future, right? But, I'm hoping in the 30s that we will really see that everything is within reach and can be proven efficiently. Okay, so that sort of like covers the brief introduction and overview of what are these succinct proofs and what is it that we care about. I want to switch gears a little now and also like sketch out how to construct a succinct proof for sort of like a toy problem. So you can sort of get an intuition for some of the techniques that people are using in this space. Okay. And the first thing I want to talk about is, so throughout the talk, I'll be constructing a lot of interactive proofs, okay? And the reason I'm going to do that is because there's a technique that can make interactive proofs non-interactive. So let me first talk about what this technique looks like and also give you sort of like a bird's eye view of what do typical proof systems look like. Okay, so take a typical interactive proof, then you will have sort of like messages from the prover to the verifier. The verifier responds with something we may call a challenge. Prover will send a message, and there may be many rounds of interaction like this. Okay, now many of the proof systems we have are what is called public coin proof systems. Okay, and what this means is that the challenges the verifier sends to the prover are independent of the prover's messages. So in other words, the prover will send some messages to the verifier, and the verifier will just generate some entropy and without even bothering to look at those messages and send that entropy back. And now the prover may send some more messages and the verifier will again just pick some random stuff and send that back as challenges. Okay, and we'll see examples of how this is a useful way and how this is useful for the verifier to actually verify the proof. But the point is here is just that let's take an interactive protocol where the verifier's challenge to provers are just randomness. Now the Fiat-Shamir heuristic then says, well, how about we replace those challenges with some outputs from a cryptographic hash function instead, right? Because what does a cryptographic hash function do? Well, it basically takes some input and then messes it up and mangles it as much as possible and tries to output something, an output that just looks like random stuff. Okay, so the way it works then is, okay, the prover will generate the first message, okay? And then we'll compute a challenge to the prover just by taking the hash of everything the verifier has seen so far, right? So you would take the instance, you would take the messages from the prover, and you would hash that. And that would be the challenge that the verifier sends to the prover. Okay? If the verifier has to send a lot of random challenges, you may then use some sort of random function and extend that randomness. Okay, now the prover generates the next message, and again, if it's multiple rounds of interaction, you would again use a hash of what the verifier has seen now and use that as the challenge, right? The point is that we're actually completely taking the verifier out of the loop, right? Because now we're just using the hash function to compute challenges. So the whole transcript can just be computed by the prover, right? And now the proof could just be, well, basically the prover messages, right? And then you can, whenever you see that transcript, you could just yourself take a hash function, compute the challenges, and then verify is this a valid transcript or not. So this means that whenever we have a public coin interactive proof system, then we can make it non-interactive with a future heuristic, right? A little care must be taken about security and so forth, right? But that's all like the general picture for these kind of proof systems. Okay, so now I want to dig a little more into how to construct these proof systems, okay? And a lot of them are based on a cryptographic scheme called the commitment scheme. So I want to talk a bit about commitment schemes. Okay, so the intuition behind a commitment scheme is that we want to get something like a commitment oracle, right? So think about this as sort of like a setting where you could, as the prover, you could say, here's a message, okay? And you could give it to the oracle, and now the oracle holds that, right? And the prover has sort of made a commitment to this message, right? But the oracle will not tell the verifier that what the message is. You just say, hey, the commitment has been made. Later on, the prover can then say, hey, I actually want to reveal this message to the verifier, right? So it could tell the oracle, open the message. And then the oracle will say, okay, here's the message, and send that to the verifier. So the commitment oracle, if we had this kind of oracle by magic, right, it has sort of like two nice properties. First of all, it's binding, right? So once the committer has sent the message, right, then can't change her mind anymore. And at the same time, it's hiding, right, because the commitment doesn't reveal the message M. Okay, this is something that's going to be important for the zero knowledge property. Okay, so in practice, how do we create this kind of commitment oracle? Well, here's an example. Okay, so think about on an input M, you just pick some randomness and then compute a hash of this message and the randomness, right? And use that as a commitment. And if you later want to open the commitment, then you would just reveal that message and the randomness. Okay, so is this binding? And it's binding in some sense, right? Because it's hard to find two valid openings with distinct messages that hash to the same thing, okay? So in other words, if the hash function is collision resistant, right, then you cannot find these kind of collisions, right? But if you actually had two valid opens of the same commitment, it would mean that they hash to the same thing, and that would be a collision. Okay, so the collision resistance of the hash function would make this commitment scheme binding. At the same time, it's also hiding, right? Because the entropy here, well, depending a little on the hash function, right? But the entropy would make the output essentially look random, okay? So in other words, if there's enough entropy, then basically the hash output will also be randomly distributed regardless of what the message is. And therefore it doesn't reveal what the message is. Okay, so let me dig a little more into this, right? So what is more formally a commitment scheme, right? So we do imagine there's some sort of setup and commitment key that specifies how it operates. So it would define what are the messages we are interested in, what is the randomness you can use, and what is the commitment that should come out of this. And then there would be a commitment algorithm that takes messages in randomness and outputs commitments. Okay, and we want it to be binding, okay? Binding could be unconditional, so that when you have a commitment, there's just only one unique message it could possibly be open to. Okay, so an example of that could be you could use an encryption scheme as a commitment scheme, right? Then, there's only one unique plain text. But it could also be computational. So we just want it to be infeasible to open it to two distinct messages, right? And this hash function example was an example of this, right? In principle, collisions exist, right? It's just hard to find those collisions. Hiding can also be unconditional or computational, okay? So unconditionally would be if the commitment reveals nothing at all about the message. And this hash function example could be an example of that, right? Because the entropy, if you have enough entropy and it exceeds sort of like the size of the output hash, right? Then, you know, there's nothing, everything will look random regardless of what the message is. But it can also be computational. So if you use an encryption scheme as a commitment scheme, right, then what you get is just a property that it's hard to distinguish one plain text from another plain text. Okay, so why am I talking about commitment schemes? Well, because a lot of them have this sort of like very common structure, right? So if you have a prover with an instance and a witness, and the verifier with instance, typically the structure is something like this. The prover will send some commitments, verifier will send some challenges. They may repeat several times this, and then the prover will send some responses. Okay, so you can think of this as like, you know, the prover has a move where it sends some commitments, and maybe, you know, depending on the proof system, but one example could be that the challenge move could be some random indices, so sort of like doing a spot checking and say, open these commitments here, right? And maybe the prover's response could then be openings of those specific commitments. And actually, this is something that people use. So if you ever heard of something called the interactive oracle proofs, that sort of like abstracts this model here, that you could have some input messages, think of those as messages you commit to, and then the verifier can make some queries and see those specific messages. Right? In principle, the verifier could ask to see all of them, but the query complexity will be sort of what ties into the verification complexity. So if we want to efficient verify, then it shouldn't ask too many indices. Okay. In interactive oracle proofs, this can happen many times. In the olden days, before interactive oracle proofs, there was this notion of probabilistically checkable proofs, which is just like a one-round IOP. So you cannot do this for multiple rounds. You can just send some input message, and that's it, and then the verifier can query some positions. Okay, so this is a very used model, but it's also a little inefficient because, well, it's not such a flexible oracle, right? You can just say, here's some messages and here's some indices, reveal those. So I'm going to talk about more powerful type of commitment scheme, namely commitment schemes that have a homomorphic property. And you could imagine that we can create more efficient proofs that way. Okay, so what is a homomorphic commitment scheme? So here the message space and the randomness space and commitment space will be groups, okay? And it will be homomorphic in the sense that you can take two commitments to two different messages, okay? And multiply them together. And inside the commitment, that gives you this homomorphic operating, and that this will be a commitment to the sum of the two messages you committed to. And we will see that this is sort of like very powerful structural property to have of a commitment scheme. So let me give you an example of a commitment scheme that satisfies this, namely the Peterson commitment scheme. Okay, so here the setup is that we have a large prime, and we have a cyclic group that has that size, and it's generated by generator G. So in other words, all the group elements can be written as a power of G. And the message space will be then integers modulo P, and the commitment scheme would be the group elements. Okay. In the setup, we will also have two group elements, G and H, and we'll assume that the discrete logarithm assumption, namely that it's hard to compute a K such that H is equal to G to the K, right? So K here is known as a discrete logarithm. Now to commit to a message, we will then pick some randomness R, and we'll compute the commitment as G to the M times H to the R, right? So that's one group element. Okay, and this commitment here is perfectly hiding, right? So it doesn't disclose the message. Well, why is that? Well, because of this H to the R, right? So H is a generator for the group. So H to the R is just completely random group element. And if regardless of what M is, when you multiply G to the M with a random group element, you just get a random group element, right? So the commitment is just, regardless of message, going to be a random group element. And that doesn't reveal anything about what the message is. It is binding, however, and this is where we use the discrete logarithm assumption. Okay, so you can show that if you can find two different openings to the same commitment, so in other words, g to the m h to the r is equal g to the m prime h to the r prime, where m and m prime are different, then you could actually break this discrete logarithm assumption. Now, this commitment scheme actually has this homomorphic property, right? Because if you take a commitment to A and B, so g to A times h to the r times g to the b times h to the s, right? So multiply those two commitments together. Well, what you get is g to the a plus b. So in other words, a commitment to a plus b. Now, this is just one example of a homomorphic commitment scheme. There are other examples, and you can sort of like, in general, for these kind of protocols, they work for any homomorphic commitment scheme, and you can sort of like just plug in, you can sort of like create information theoretically, what is the proof system you want. If you have a homomorphic commitment scheme, then you can plug in your favorite homomorphic commitment scheme to actually get a cryptographic proof system. Okay, so I'm going to look at some very simple statements in this toy example. I'm going to be interested in, does a commitment have zero as the message, right? So is it a commitment to zero, or is it a commitment to something else? Okay, so in other words, the statements will be informed. The commitments belong to this language, which consists of commitments to zero. Okay, and let us for the moment just assume this is a perfectly binding commitment scheme, right? So there's some unique M inside a commitment, right? But it's hiding, so it's hard to tell if M is zero or something else, right? So in other words, it's hard to decide whether the statement is true or false. So there's something interesting to prove here. So I'll illustrate, sort of like give the first proof system here with something which is a very common pattern known as a sigma protocol. Okay, so it works like this. We have this commitment here, right? And the claim is that it is a commitment to zero. Now the prover will pick another commitment to zero at random and send that to the verifier. And then the verifier picks a public coin, right? It's just a random challenge, so just a random element integer modulo p. It sends that back to the prover. And now the prover computes a respond t, which is equal to rx plus s, right? So basically a linear combination of the randomness used in the original commitment C and in the new commitment picked by the prover called D. Now the verifier then will do a simple check, namely if the commitment C and D satisfy that C to the x times D is a commitment to zero with the randomness T, then we'll say yes, I accept the proof. I believe that C is in the language, that it's a commitment to zero, and otherwise it will reject the proof. Okay, so we want this to be a proof system, so let's first check that it's complete and sound. Okay, so for completeness, well, let's just compute what is it the verifier is checking. Well, that Cx times D is equal to something, right? So, well, what is C? That's commitment to zero with a randomness R. If we raise that to X and multiply that with D, which is commitment to zero with randomness S, then by the homomorphic property, that's the same as a commitment to zero, and Rx plus S. And Rx plus S was exactly the T that the prover sent, right? So the verifier will accept this proof. It actually has perfect completeness. It will always be accepted when the prover is honest. Okay, now let's think about soundness, right? And here we should think about a prover that doesn't have a witness, right? The prover is trying to cheat. Okay, so the verifier is just interacting with something that sends some D, right? And then the verifier will send back a random challenge X, and then we'll get back some T, which is an integer modulo P. And then do the verification check, right? The C to the X times D, a commitment to zero with randomness T. Okay, so let's look at this here, right? So the test Cx times D, well, now we don't know anything about C. It's just some commitment to some A, right? But we don't know whether A is 0 or not. Okay, and D is just some commitment to some B, but again, we don't know anything about B. Okay, but what we do get from the homomorphic property is that this will be a commitment to AX plus B, whatever A and B are. Okay, and with randomness Rx plus S. Okay, the point is that, well, if A is not 0, right, and you pick X at random, then the probability that AX plus B is equal to 0 is going to be very small. It's actually going to, there's only going to be one possible X where it could be 0, right? In most cases, it will not be. Okay, so this kind of random spot check by just picking a random element integer modulo P is something that gives the prover very low probability of actually being able to fool the verifier. So I want to illustrate that visually as well, right? So you can think of the instance C and the prover's initial commitment D as committing to some arbitrary A and B, right? But it does implicitly define this committed line that the verifier will check in the verification equation, namely AX plus B, right? And what really happens here is that you could think of the verifier essentially saying, okay, now the prover's messages give me this line. Now I'll check it at a random X coordinate X, okay? And check that it evaluates to 0. Now, if the line is Y equals 0, so in other words, A is 0 and B is 0, then good, it will always evaluate to 0. That was completeness, right? But if it's a non-trivial line, if it's not 0, if A is not 0, then you have a line with a slope, right? And you can only intersect the X coordinate, X axis in one point, right? So if the verifier is very unlucky, it will pick exactly that point. But in most cases, the verifier will not be picking that point and will catch the cheating prover. Okay, so we've sort of convinced ourselves that this is complete and sound. Now let's think about privacy. Is it zero knowledge, right? So I'll show you that it's honest to verify zero knowledge. And basically, the reason it doesn't, this interaction with an honest prover doesn't give the verifier any extra information is because the verifier could actually simulate the entire transcript itself. Basically, the way you can do that is just by doing things out of order, right? So you can simulate by picking T first at random, and then X at the random, and then you can compute this D as a commitment to 0 with T times C to the minus X. Now, okay, if you look at that in D, right, it would satisfy the verification equation that verifier had. It would be sort of like a valid transcript. And you can actually argue that that looks exactly like an honest transcript where the verifier is interacting with an honest prover, right? Because X is random, just as in an honest transcript. And T is also random, just as it would be in an interaction with an honest prover that had picked an S at random. Okay, so this looks exactly like an interaction with an honest prover, right? And the reason that you can simulate is just you can do things out of order. And the reason the prover cannot cheat is because, well, the prover is forced to first send D and then respond to a challenge. Okay, so I want to go back a little to this question of soundness, right? Because I said, well, if it was perfectly binding commitment scheme, right, then there's a unique message and it makes a lot of sense to ask, is the message 0 or is it something else? But if it's not perfectly binding, just computation binding, but perfectly hiding, right, then actually a commitment could be both a message 0 with some randomness and message 1 with some different randomness and a message 2 with some second randomness and so forth, right? So actually for something like the Peterson commitment, then this claim that a group element is a commitment to 0 is trivially true, right? There is some randomness that makes that true. So it doesn't make so much sense to talk about soundness, okay? And that's sort of like sad, but we can actually say something more strong about than soundness that does make sense also in this setting. Okay, So I want to say that sigma products can, in general, have a stronger soundness property called special soundness. So think about here, we have a statement C, which is claimed to be a commitment to 0, right? And the prover has sent message D, okay? Now there can be sort of like two settings, right? Either the prover has very low probability of convincing responding to a verifier challenge, okay? In that case, well, we don't care so much, right? It's not going to convince the verifier, so we don't have to worry about soundness. If, on the other hand, it has high probability of convincing the verifier in a random challenge, well, then we could actually imagine sort of like, saying, well, if you can answer this challenge and that challenge and so forth, right, then we could actually have answers to many challenges, okay? So suppose now we have answers to two different challenges, x and x prime. What does that give us? Well, we know from the verification equation that Cx times D should be a commitment to the response to the first challenge, and Cx prime times D should be a commitment to 0 with the second response, right? Now, if you sort of like divide one of those verification equations with the other verification equation, the D's cancel out. And what we have is C to the x minus x prime is a commitment to 0 with randomness t minus t prime. Okay? And that means that we actually get an explicit opening of the commitment. The commitment is a commitment to 0 with randomness t minus t prime divided by x minus x prime. Okay? So it's sort of like, not only is the statement true if the prover can convince the verifier, but we can actually, from multiple answers, we would actually be able to extract a witness. And we call this that it's a proof of knowledge, okay? So standard soundness just says we cannot convince a non-verifier if the instance is false, right? But knowledge soundness says something stronger, that if the prover can convince the verifier, then we can actually extract an explicit witness, okay? So knowledge soundness captures that you have this kind of extractability property. Okay, often when people describe this, and informally they say the prover knows a witness, okay? That's a proof of knowledge says that essentially says that a prover knows a witness. I think I'm a little hesitant to endorse that way of describing it, because one has to be very careful about what the prover is, right? So imagine the prover is, we have this isolated machine that acts as a prover. It's inside a trusted execution environment. We have like put it in Faraday cage and so forth. Okay, and now we sort of like interact with it and we get convincing proof. And we could imagine if we could sort of like freeze the state and run it again, we could get answers to different challenges. We could extract a witness. Okay, and also like acknowledge that, this kind of isolated prover has, it's possible to extract the witness. So in some sense, it knows a witness, right? But a priori, the verifier doesn't know that, right? I mean, if you're talking to somebody over the internet, right, you're just seeing messages coming back and forth, right? We cannot assume that there's some isolated prover, right? It's more like this is like whatever entity is giving us messages, and it might be some adversary that's interacting with the rest of the world over the internet and so forth, and might be some third party and it's just the man in the middle or something like that, right? So one has to be very careful about the meaning of prover when we talk about the prover knows a witness. So I prefer to think of knowledge soundness and a proof of knowledge as a proof system where, in principle, a witness is extractable. Okay, so I want to go into now succinct proofs. So let's take a slightly more complicated type of relation. Let's suppose we have n commitments, right, and claim all of them are commitments to 0. And it turns out that we can actually extend exactly the same protocol as before to cover this case in a fairly simple way. Okay, so we'll again just the proof will send a commitment to 0 with some randomness s. The verifier will pick a random challenge, but now we will create this kind of polynomial in the random challenge, and the prover will send that to the verifier, evaluate that, and send that to the verifier. Okay, and then you can do this kind of a check. Now it's sort of like we're checking something with all of the commitments in the instance, of course, right? And we're checking that this evaluation still gives us a commitment to 0. Okay, so you can sort of like look at that a bit, convince yourself that it's complete, and indeed the T is correct and would convince the verifier. Okay, so let's think about soundness here. Okay. Okay, and first of all, let me say, why did I pick this example? I think it's an interesting example because it's a succinct proof. Okay, you have a size n instance, right? But the proof transcript is just the single commitment D, a challenge X, and a single integer modulo PT. Okay, so it's a very small proof, but potentially a very large instance. Okay, so let's sort of like intuitive say, why should this be sound, right? So again, imagine for the time being just that it's a perfectly binding commitment scheme, so these messages are well defined. Okay, so suppose messages inside the commitments in the instance are A1, A2 up to AN. Okay, and then D has the message B inside it. Okay, what the verification equation really defines is this committed polynomial, where it's the sum of the AIs multiplied by powers of X to the I. Okay, and then the verifier will pick at a random point and check that this polynomial evaluates to 0. And as you may know, then if we have a non-zero degree n polynomial, then it can have at most n roots, right? So in other words, if the polynomial is just 0, if all the AIs are 0 and B is equal to 0, then Y is just 0, and no matter which challenge X the verifier picks, then yeah, you will indeed get 0. However, if one of the AIs or more of them are non-zero, right, then you have a degree n polynomial which can have at most n roots. And again, it's very unlikely that the verifier will pick one of those n points rather than just something else when it picks at a challenge at random. So really what's hiding inside this batch proof is that we're doing some checking that a polynomial is equal to 0 just by picking a random point and evaluating the polynomial in that point. And this is a pattern you will see in many of the proof systems, I think, in the rest of the bootcamp. Okay. So more precisely, right, we often refer to what is known as the Schwarz-Sippel lemma, which says that if you have a non-zero polynomial, then the probability that it evaluates to 0 is at most n divided by p. Okay, let's see. So, okay, I want to spend one more moment on this slide here, right? And I want to note that while the proof communication is very small, we're just sending 3 elements, right? Then the verifier still does a lot of computation, which is sort of like on the order of size n, right? Because you're computing this exponentiation here, right, of the commitments from the instance, right? And you're doing something with each one of them. Okay, so this computational effort of the verifier is of size O of n. So the question I'm going to ask now is, can we also have sublinear cost for the verifier? Okay, so let's return to commitment schemes, okay? And think now of commitments to vectors instead of single integers modulo p, okay? And we could imagine having a commitment scheme to vectors, which is also homomorphic, right? And at the same time, it might also be a succinct commitment scheme, right? So an example of that would be a generalization of the Peterson commitment scheme. So now we have k+1 group elements in the setup, and the commitment algorithm to commit to A1 through AK would basically be a product of these group elements raised to the respective A's. Okay, so in other words, even if you're committing to a large vector of integers modulo P, right, then you're just getting a single group element out of the commitment. So this is sort of like a succinct type of commitment scheme. Now imagine we have a succinct type of commitment scheme, right? Now we could have a relation where we're saying here's a bunch of commitments and all of them are commitments to 0 vectors, right? So the total size of the claim we're making is that we have k times n zeros inside these commitments. Okay, so what is the protocol? Well, it looks more or less like it did before. We'll just the prover will commit now to a 0 vector and send that to the verifier. The verifier picks a challenge. The prover corresponds with the same challenge as we did before in the batch proof. Okay, and the verifier checks that indeed this product here is a commitment to a 0 vector with randomness t. Okay, you can again check completeness as we did before, and it will also have soundness as we showed before. Okay, I'll not go into the details of that, but I want to sort of like highlight here, right, that not only is it a succinct proof because it has very little communication, but actually the verifier only does O of n work, right, when it checks the verification equation. But this is actually a proof of knowledge of k times n field elements being equal to 0, so, right? So now there's some sublinearity in the verifier's effort as well. Okay, so I want to sort of like zoom out, and thanks for your attention so far. So what I did is I outlined sort of like a SNARK, right, where I wanted to get to the point that it's succinct, right, and we have seen that it sort of like has very small amount of communication, okay, and very low verification cost compared to how many zeros are committed. Okay, it is an argument of knowledge, right? So we talked about the special soundness and how that sort of like indicates that it's an argument of knowledge. Actually, in the batch proofs, what we would get is sort of like an n special type of soundness, right? So you need sort of like responses to n+1 challenges, and then you would be able to extract all the witnesses. And it's non-interactive, right? So remember, we could use the Virchow heuristic because this is a public coin protocol. So that gives us an example of a SNARK. Okay, and I think in the rest of the bootcamp, you can then look forward to sort of like all the other questions you may have now, right? I mean, you could say that proving having a commitments to a bunch of zeros is not so interesting. So can we prove interesting statements that actually talk about general purpose computation? And the answer to that is yes. There's a lot of intricacies involved in that. And then also you can ask questions like, you know, actually how much can we push efficiency, right? So how succinct can the SNARKs be? How cheap can the verifier be? How cheap can the prover be, right? And you'll also like see, I think, along the way that it's quite impressive what we can do, right? So nowadays we actually have these SNARKs where they can be really small in terms of communication, very cheap to verify, and much less effort than if you wanted to sort of like just take the witness and check yourself that this instance is in the relation, right? And we're also seeing now that in theory, we have known for several years now that the prover can be linear time in sort of like the size of the computation, okay? But the question then has been also what is the constant there, right? And that's been a horrible constant, so like in the ballpark of 1 million or above. But now we're seeing like improvements every year, and you know, a lot of people doing research in this space. So I think we'll see increasingly cheap provers. And I think one exciting technique there is so like GKR, which is underpinning Expander. right? And the reason it's exciting is that you can sort of like, I mean, you do need some commitments to some base data, but then after that, you can actually do a lot of the reasoning about the committed values and that they actually sort of like are valid. You can do that without sending more commitments. So you're sort of like taking out the cost of commitments in the equation, and you're just actually doing a lot of operations of these integers, integers modulo p, or more general in some sort of field. So yeah, thanks a lot for your attention. I'm personally looking forward to the workshop, and now I'll take some time to look at all the questions that you may have asked along the way.
Hey, Jens, that was great. First thing that all of the questions we've received is about the slides. Slides were amazing, a lot of useful information, which we'd love to provide. So we will be in touch through Eric as well, if you can provide us with a copy of the slides, and we will make sure to distribute it with everybody else. Also, a note for everyone that is still watching, a recording of this course, this session will be made available tomorrow. So in the next 24 hours, we will also add it to the Hacker Pack, so you will be able to rewatch it and look at the slides as Jens provided to us. Right, we have a few questions, Jens. You can click on the questions area and address them as you see them.
Absolutely, right. So the first question is in terms of course book or other study material. And I have to say that there's a lot of material out there. So I think there's sort of like MOOCs. I have not looked so like closely at them myself. It's sort of like, what is sort of like good introductory material, but I know there's a lot of online lectures and so forth that you can find. If you sort of like, if you really want to dig deep into sort of like the math and sort of like get sort of like really up to speed with sort of like modern zero knowledge proofs, I recommend the book by Justin Thaler, which is available online. Okay, let's see. Link to the slides. We will provide the slides. Yeah. Okay. And let's see. So then there's a question about the trust and security assumptions in sort of like the pre-setup phase, where we have these pick typically group elements, and typically they would be picked on an elliptic curve, right? So in the olden days, you used so like exponentiation. This is where the exponentiation notation comes from. You used exponentiations in a field of like enormous size. Nowadays, people use elliptic curves to generate these groups because that gives you a much smaller representation, more efficient computation. And the nice thing about the Peterson commitment scheme is that you don't actually need to put trust assumptions in it. So you do have to assume that it's an elliptic curve, which is secure, and the discrete logarithm problem is hard, right? So you would be trusting, typically it's sort of like a standards committee or something like that. You would pick the setup that they have chosen, so you would have to trust that. And okay, and a few small traps you can fall into picking an insecure elliptic curve. But the group elements in themselves, you can actually generate them in a way that seems trustworthy, and where it's unlikely that you can compute the discrete logs. The idea is basically you take a hash function and you hash into the curve. So you try some hashes for an x coordinate of the elliptic curve point, and once you get lucky, you get something on the curve. Then that's your first group element, and then you continue and find that second group element, and so forth, right? And by this process, which is really randomized and outside your control, it's unlikely that you can find any discrete log relation in them. So you can use a trustless setup with a Peterson commitment, and you can also construct other types of homomorphic commitment schemes. You can also get homomorphic commitment schemes just from hash functions if you allow some interaction, right? Again, then you're just trusting that the hash function is collision resistant, right? Which is sort of like a standard assumption. So for the things that I was talking about, you don't actually need a trust in a third party to generate the setup. Okay, so let's see. Okay, I think that was the question channel. Let me see if there's anything else in the chat. Okay, thanks Shenfei for providing the link to the book. Okay, I think, let me see. Okay, I don't see any other.
Yeah, Shenfei has been really helpful in chat and providing a lot of
excellent
information and following up on all technical bits. So I think the majority of the topics have been covered from the chat section. So I think last thing, and a new question came in from Sebastian. Maybe fit that one in the questions tab.
Okay, let's see. Why the soundness property? Let's see. Let me see. So that sounds like something which is specific to one of the schemes I presented. So like I did go through the soundness for and the special soundness of this, or like the case where you have a commitment to a single zero and you want to prove that this is a commitment to zero, right? So there it's basically because, well, if the prover could answer two different challenges, then you can actually extract some randomness that shows this is the instance is a commitment to zero. Okay, so for the other schemes, right? So roughly speaking, the intuition is that if you have a batch proof where you have several commitments, you're claiming all of them are commitments to zero. So what you can do is actually, if you have, now you're saying, okay, if the prover could answer n+1 challenges, then you could actually extract the contents of every single commitment, and you would see that it was zero, right? And intuitively, the reason is, so think about special soundness. If you just have one commitment you're proving has zero, right? So you're basically forming this line here, right, by the instance commitment and then the commitment that the prover sent, right? And if you pick 2 points on the line and you get what are the values there, then you can actually determine the slope and the offset of the line, right? So you know and that's sort of like the defined by those messages. Okay. Intuitively, if you have n commitments, then you get this degree n polynomial. And if you can pick n+1 points and get the evaluations on that polynomial, then you can determine the full polynomial, okay, using Lagrange interpolation. So that's sort of like the intuition why also in the case where we have batch proof that it's also proofs of knowledge, right? So, but sort of like a more generalized type of n special soundness.
And there's okay. If you have the time to answer as well.
Sure. Let me take this one. So here, right? So in bullet proofs, after tensoring, we can produce multiple proofs for single commit made by not shuffling constants in linear times. Okay. I'm not sure I understand the question here. But let me. But maybe I can start by giving a bit of context just on bullet proofs, and then I guess maybe Hasib can clarify the question, right? So these are sort of like proof systems where you do some. So basically, let's see, how do we explain this? So with the batch techniques I presented, you can prove things about, you can get proofs that have roughly square root size, right? So if you have like vectors and you have a bunch of commitments, you can sort of like prove things with a complexity that depends on the number of commitments and the size of the vector, and you get then down to square root size. I see. Okay, so I guess you clarified the question along the way. Okay, so well, anyway, for context, in bullet proofs, then you can actually have even bigger commitments, okay? But you sort of like do some maneuvering around to whittle them down, so you actually get logarithmic complexity instead. Okay, now Hasib's question is, okay, is there a use case for multiple proofs for a single commitment? So that's actually a pretty good question. I think maybe you actually what it aims at is, so there's this notion of commit and prove schemes. Okay, so the idea is, if you have put in the effort to create some commitments, right? Then, let's reuse them if we can. And maybe a commitment represents some data that's important, which appears in one context, a different context, and third context, right? So you would actually have the same commitment in sort of like multiple types of instances and claims about those instances. And there are sort of like ideas for, sometimes you can, get, create these proofs a bit more cheaply if you already have these commitments prepared and you don't have to recommit to that data. So I do think that there's a use case where you would actually have, one commitment or a set of commitments, and you would actually, they would appear in different contexts, and you could maybe reuse the same commitments and prove things about them. So that's, yeah, a good point.
All right. So everybody, thank you so much. I think we are a bit over time, but I think everybody enjoyed this. Again, there's been a lot of questions and things that needed to be clarified. Thank you, gents, for sticking with us and providing additional information for everybody. Again, everything will be provided to everyone. You will be getting a copy of the slides as well as a recording. You'll be happy to follow through, and we will be coordinating on adding additional reading materials throughout the bootcamp. So I know some of the things you might be looking for might not be in a hackerback at the moment, but as we speak, and we're still in communication with a lot of the speakers, we will be adding a lot of useful information for everybody. That being said, any last words, Jens? Something to say goodbye with?
Just thanks to everybody for your attention, and thanks for the questions.
Thank you so much for being here. Thank you all for being and attending the launch event as well as the very first workshop. We will be having a pause tomorrow. There will be no workshops as of right now, but on Wednesday, we will be having 2 workshops. The first of which will be on post-quantum aggregatable signatures, and morning, which will be from Dimitri from the Ethereum Foundation. And after that, we will have a workshop from Dan Pone from Stanford. Topic to be clarified as well. Invite should be in your calendar. We will be sending you reminders. If not, as always, please make sure to DM me on Discord or on Twitter. I'm always around. Me and my colleagues will be happy to help you out. And yeah, looking forward to seeing you all on Wednesday. Have a great day, and thank you for coming. Thank you, gents.